Imagine an asteroid moving through the gravitational field of a planet. We use calculus to understand what happens to its velocity. How much will the asteroid accelerate? How fast can it become? To answer that, we first need a basic idea from mechanics. Newton's second law connects force and motion. In Newton's original wording, motion means what we now call momentum. Momentum depends on the amount of matter in a body, the speed at which the body is moving, and the direction in which it is moving. In modern notation, momentum is a vector quantity, defined as mass multiplied by velocity. This means momentum depends on mass, speed, and direction. Because velocity has direction, momentum has direction too. Newton's second law says that force is the rate at which momentum changes with time. In calculus language, force is the time derivative of momentum. Now, let's apply this to an object with constant mass. Since momentum is mass multiplied by velocity, we can substitute it into Newton's second law. Because the mass is constant, it does not change with time. So we can move the mass outside the derivative. The derivative of velocity with respect to time is acceleration. So Newton's second law becomes the familiar formula. This means force changes velocity. In a gravitational field, this force is gravity. The gravitational field affects our asteroid by doing work on it. Work is the energy transferred to or from an object by a force acting along a displacement, the dot product. If the force points along the displacement, the object gains kinetic energy. If the force is perpendicular to the motion, it does not change the speed, but changes velocity. Now imagine the asteroid moves along a path. The force becomes stronger as the asteroid gets closer to the planet. It has an inverse square relation with distance. So we cannot always use one force multiplied by one distance. Instead, we divide the path into many tiny displacements. For each tiny displacement, we calculate a tiny amount of work. Then calculus adds all these tiny pieces together. That is why work is written as the integral of force dotted with displacement along the path. Now we connect this to velocity. Velocity is displacement per unit time. So a displacement can be written as velocity multiplied by a time step. Instead of force dotted with displacement, we can write force dotted with velocity. Now we use Newton's second law. For an object with constant mass, force equals mass times acceleration. So work becomes the integral of mass times acceleration dotted with velocity over time. Acceleration is the change of velocity with respect to time. So the expression becomes mass times the integral of the velocity derivative dotted with velocity over time. Now comes the key step. During a tiny time step, acceleration creates a tiny change in velocity. So acceleration multiplied by a tiny time step gives a tiny change in velocity. This lets us change the integral from time to velocity. For straight line motion, where acceleration and velocity point along the same line, the vector expression becomes simpler. Acceleration dotted with velocity becomes speed multiplied by the rate of change of speed. So the work becomes mass times the integral of v dv. Now this integral is simple. The integral of v dv is 1/2 v squared. So the work becomes 1/2 mass times final velocity squared minus 1/2 mass times starting velocity squared. This means work is the change in kinetic energy. So calculus gives us the formula for kinetic energy. Work transferred by force becomes motion stored as kinetic energy. Now we apply calculus to gravity. Newton's law of gravitational interaction describes the force between two masses. Strictly speaking, both objects attract each other, and both objects can move. But for this model, we choose the planet as the origin of our coordinate system. So we describe the asteroid's motion relative to the planet. The distance r is the distance from the center of the planet to the center of the asteroid. Newton's gravitational formula gives the size of the force. The force equals g times the planet mass times the asteroid mass divided by r squared. Here, g is the gravitational constant, the planet mass is capital M, the asteroid mass is small m, and r is the distance between their centers. This formula tells us that gravity becomes weaker with distance. When r becomes larger, r squared grows even faster, so the force becomes smaller. But r cannot be 0, because division by 0 is undefined. Physically, this also tells us that we must be careful with the meaning of r. For a planet and an asteroid, r is not the height above the planet's surface. It is the distance from center to center. This also reminds us that Newtonian gravity is a classical model. Now we want to find the work done by gravity. For a constant force, work is simple, but gravity changes with distance. So as before, we use integration. Work equals the integral of force dotted with a tiny displacement vector. The dot product is important. It means that only the part of the force pointing along the motion does work. Now let us combine the two conclusions we obtained for work. On one side, we have the work done by gravity. Work done by gravity is the integral of the gravitational force vector dotted with the tiny displacement vector. The gravitational force vector is minus gmm divided by r squared multiplied by r hat. The minus sign means gravity points towards smaller r. So the gravitational work expression is the integral of minus gmm divided by r squared times r hat dotted with dr vector. On the other side, we have the work and kinetic energy result. Work is equal to mass times the integral of velocity vector dotted with a tiny change in velocity vector. So we set these two work expressions equal. The gravitational work expression equals m times the integral of v vector dotted with dv vector. Now we simplify the equation for radial motion. Radial motion means the asteroid moves directly toward the planet or directly away from the planet. In that case, the tiny displacement vector points in the r direction. So dr vector becomes dr multiplied by r hat. Now look at the dot product. The gravitational force contains r hat. The radial displacement also contains r hat. And r hat dotted with r hat equals 1. So the vector expression becomes a scalar expression. The left side becomes minus gnm times the integral of dr divided by r squared. On the right side, if the motion is along one line, v vector dotted with dv vector becomes v dv. Now we apply limits. The distance changes from r0, the starting distance, to rf, the final distance. The speed changes from v0, the starting speed, to vf, the final speed. Now we integrate both sides. The integral of 1 over r squared gives minus 1 over r. The integral of v dv gives 1/2 v squared. This equation connects gravitational work with the change in kinetic energy. Now consider the special case. The asteroid starts from rest very far away. So r0 approaches infinity, and v0 is 0. The asteroid falls to the planet's surface. So the final center-to-center distance is approximately the planet radius. We call this final distance r. In this case, 1 over r0 approaches 0, and v0 squared is also 0. So the equation becomes gmm divided by r equals mvf squared divided by 2. Now the asteroid mass appears on both sides, so the asteroid mass cancels. After rearranging, we get vf equals the square root of 2gm divided by r. This gives the speed reached by an object falling from rest from very far away. Now, let us evaluate this for Earth. We use the gravitational constant, we use the Earth mass, and we use the Earth equatorial radius. Substituting these values into the formula gives 11,180 meters per second, or 11.18 kilometers per second. So an object starting from rest very far from Earth would reach approximately this speed when falling to Earth's surface, if we ignore all other forces except Earth's gravity. By energy conservation, this same value is also the escape velocity from Earth's surface, ignoring atmosphere and Earth rotation. Now, let us compare this speed with something familiar. A passenger airplane usually flies at about 900 kilometers per hour. That is about 0.25 kilometers per second. But our calculated speed is about 11.18 kilometers per second. So the falling asteroid would be more than 40 times faster than a passenger airplane. This is far above Mach 5, the usual boundary for hypersonic speed. Mach 5 is roughly 1.7 kilometers per second, depending on altitude and air temperature. At hypersonic speed, the air in front of the object cannot move away fast enough. The gas is compressed extremely quickly. This rapid compression is close to adiabatic compression, meaning the gas heats up before it can transfer heat away. At 11 kilometers per second, this heating becomes extreme. A strong shock wave forms in front of the object. The surrounding air can become glowing plasma. The object's surface can heat up, melt, vaporize, and ablate. Ablation means that material is removed from the surface by extreme heating and high-speed flow. So yes, This speed is absolutely enough to create visible atmospheric entry heating. In everyday language, we often say the object is burning in the atmosphere. More precisely, it is not ordinary fire. It is extreme aerodynamic heating, shockwave heating, plasma formation, and surface ablation.